Tonight we're going to explore something that should truly and deeply terrify you. Not because it's likely to happen in your lifetime, not because you need to prepare for it, but because when you truly understand what would happen if our sun slowly went dark, it fundamentally changes how you see absolutely everything around you. Your morning coffee, the plants in your yard, this warmth on your skin, the very air you breathe, all of it depends on one single thing. A ball of fusing hydrogen 150 million kilometers away that has been burning steadily for 4.6 billion years. And here's what most people don't fully and truly realize. If that ball of fire started to dim, started to fade, started to slowly go dark completely, Earth wouldn't just get cold, it would die. Completely, utterly, irreversibly. And by the end of this deep exploration, you're going to understand exactly why every single living thing on this planet exists at the pleasure of our star, and why we are far more fragile than we'd like to believe. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive into what would actually happen if our sun started to fail. Let's begin with something you take for granted every single day: sunlight. Right now, as you watch this, our star is doing something extraordinary, something so powerful, so violent, so intensely energetic that if you truly understood it, you'd be amazed we can casually walk around under it without a second thought. The sun is converting 600 million tons of hydrogen into helium every single second through nuclear fusion. Think carefully about that number for just a moment. 600 million tons. Every second, not every hour, not every day, every single second. That's roughly the mass of a mountain being transformed from one element into another through the sheer pressure and temperature at the sun's core. The core temperature reaches about 15 million degrees Celsius. Try to comprehend that. The hottest temperature ever achieved on Earth in a laboratory is about 4 trillion degrees Celsius for a fraction of a second in particle accelerators. But that's an artificial, momentary spike. The sun maintains 15 million degrees continuously in its core, a region about 25% of the sun's radius from its center. In this inferno, hydrogen atoms are moving so fast, colliding with such energy, that they overcome the electromagnetic force that normally keeps them apart. They fuse together, combining into helium atoms, and in that fusion, a tiny amount of mass disappears, converted directly into energy according to Einstein's equation E equals mc squared. And that process, that ongoing thermonuclear reaction happening 150 million kilometers away, releases energy, an incomprehensible amount of energy. Try to visualize the most powerful thing you've experienced. A thunderstorm, maybe. Lightning strikes carrying millions of volts, releasing enough energy in a fraction of a second to power a home for a month. Or a rocket launch, the raw power of controlled explosions lifting hundreds of tons of metal off the ground, each second of burn consuming tons of fuel. Or a nuclear power plant splitting atoms to generate a gigawatt of electricity, enough for a city of millions. Now multiply that by numbers so large they lose meaning. Every second, our star releases the equivalent of about 4 million tons of matter converted directly into pure energy. 4 million tons. That's about the mass of a large mountain, just vanishing from existence as mass and reappearing as electromagnetic radiation. That energy radiates outward in all directions as light, heat, ultraviolet, infrared, radio waves, X-rays, gamma rays, the entire electromagnetic spectrum streaming away from the sun at 300,000 kilometers per second, the speed of light. Most of that energy, the vast majority of it, perhaps 99.999999% or more, disappears into the emptiness of space, It spreads outward in an expanding sphere, diluting across the cosmic void, never hitting anything, never warming anything, never interacting with matter at all. It just travels forever through the universe, fading into the background radiation. But a tiny fraction, an almost infinitesimally small percentage, happens to strike Earth. Our planet, a sphere with a cross-sectional area of about 127.4 million square kilometers when viewed from the Sun, intercepts perhaps 1/billionth of the Sun's total output. 1/billionth. Think carefully about that. We get 1/billionth of what the Sun produces. Everything else misses us entirely, spreading out into the solar system, into interstellar space, into the galaxy, lost forever to the void. And yet that tiny fraction, that 1/billionth, is everything. It's absolutely everything. It's the warmth you feel on your face when you step outside on a sunny day. That sensation, that pleasant heat soaking into your skin. That's photons that left the Sun's surface 8 minutes and 20 seconds ago, travelled 150 million kilometres through the vacuum of space, passed through Earth's atmosphere, and struck your skin, transferring their energy to your molecules, making them vibrate faster, which your nerves interpret as warmth. It's the energy that plants capture through photosynthesis and transform into chemical bonds in sugars and starches, which then flow through food webs to feed the entire biosphere. Every calorie of food you've ever eaten traced back ultimately to photons captured by plants or photosynthetic bacteria. It's what drives our weather system. The sun heats the equator more than the poles because of the angle of sunlight. That temperature difference creates pressure differences in the atmosphere. Air flows from high to low pressure. That flow is wind. The sun evaporates water from the oceans, creating clouds which precipitate as rain and snow. This sun powers the ocean currents through differential heating. The sun drives the water cycle, the carbon cycle, the nitrogen cycle, every biogeochemical cycle on Earth. It's what keeps water liquid instead of frozen solid. Earth's average surface temperature is about 15 degrees Celsius, or 59 degrees Fahrenheit. Without the sun's energy input, without that constant flow of warmth, Earth's temperature would plummet to perhaps minus 270 degrees Celsius, just a few degrees above absolute zero, the temperature of the cosmic background radiation left over from the Big Bang. The sun delivers about 1,361 watts of power to every square metre of Earth's surface that directly faces it. That's the solar constant, measured at the top of the atmosphere before any is absorbed or reflected. 1,361 watts per square metre. That's roughly the power of a small space heater. Picture a space heater. One of those portable electric ones you might use to warm a cold room. It might draw 1,000 to 1,500 watts of power. Now imagine one space heater for every square metre of the sunlit side of the planet. Every square metre. Not just land, but oceans too. Not just at the equator where the sun is overhead, but averaged across the entire hemisphere facing the sun at any given moment. The total cross-sectional area of Earth that intercepts sunlight is about 127.4 million square kilometres. That's 127.4 trillion square metres. Multiply that by 1,361 watts, and you get about 173.5 petawatts of power delivered to Earth from the sun. Let's round to 174 petawatts for simplicity. That's 174 followed by 15 zeros, 174 quadrillion watts, continuously every second of every day, for billions of years without interruption. To put that in perspective, all of human civilization, every power plant, every vehicle, every factory, every device we've ever built uses about 18 to 20 terawatts of power. The Sun delivers nearly 10,000 times that much energy to Earth alone, and it does so effortlessly as a tiny byproduct of fusion reactions in its core. And here's the thing, here's what you need to burn into your mind. We evolved for this. Every living thing on Earth evolved in a world where the Sun delivers exactly this amount of energy. Not more, not less. This precise amount. Our bodies, our metabolisms, the biochemical reactions in our cells, they all expect this energy input. Our ecosystems, from tropical rainforests receiving intense sunlight near the equator to Arctic tundra receiving weak angled sunlight near the poles, they're all calibrated to this energy flow. The temperature of our planet, averaging about 15 degrees Celsius globally, exists in a delicate equilibrium maintained by the steady influx of solar energy balanced against the heat Earth radiates back into space as infrared radiation. The composition of our atmosphere, 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, traces of water vapor, neon, helium, methane, all of it exists in a balance that depends on this energy. Nitrogen-fixing bacteria need energy from ecosystems powered by the sun. Oxygen is produced by photosynthetic organisms as a waste product. Water vapor cycles through evaporation and precipitation driven by solar heating. The liquid water in our oceans, covering 71% of Earth's surface to an average depth of 3.7 kilometers, remains liquid because the sun keeps the temperature in the right range. Not too hot like Venus where water boiled away billions of years ago. Not too cold like Mars where water exists as ice in the soil and polar caps. Just right. The Goldilocks zone. This habitable zone around a star where temperatures allow liquid water. Think about that. Really truly think about it. The difference between liquid water and ice is just a few degrees Celsius. 0 degrees Celsius is the freezing point of pure water at sea level. Below that, water solidifies. Above that, it remains liquid. That's a tiny window on a cosmic temperature scale. And that liquid water is essential for life as we know it. Life needs liquid water. Not ice where molecules are locked in crystal structures and can't move or react. Not vapor where molecules are too far apart and too energetic to form stable structures. Liquid water where molecules can move, where chemistry can happen, where cells can function, where life can exist. And that liquid water exists on Earth because we're in the habitable zone of our star. We orbit at 1 astronomical unit, which is specifically defined as 149.6 million kilometers, the average distance from Earth to the Sun. Venus orbits at 0.72 astronomical units, too close. Surface temperature around 465 degrees Celsius, hot enough to melt lead. Mars orbits at 1.52 astronomical units, too far. Average surface temperature around minus 60 degrees Celsius. Earth at 1.0 astronomical units is just right. And the Sun is exactly the right type of star, a G-type main sequence star with a surface temperature of about 5,778 Kelvin to maintain that habitable zone at Earth's distance. So what happens when that energy starts to fade? What happens when our star, for whatever reason we'll explore later, begins to dim? Not suddenly like a light bulb burning out, not catastrophically like a supernova, but slowly, gradually, inexorably. Let's walk through it step by step, stage by stage, and I want you to really try to imagine each one. Try to picture what it would look like, what it would feel like, what would happen to Earth and everything on it. Because this thought experiment, this exploration of what we depend on, reveals something profound about our existence that most people never consider. We are not independent. We are not self-sufficient. We exist in a state of total dependence on a star. Let's start small. Let's say the sun begins to dim by just 1%. Just 1%. A reduction so slight you might not even notice it with your naked eye. You wake up one morning and the sun has lost 1% of its brightness overnight. It would still look bright, still appear as the brilliant disk you're familiar with, still painful to look at directly. The sky would still be blue during the day because of Rayleigh scattering, where shorter wavelengths of light are scattered more than longer ones, making the sky appear blue. It would still be black at night, studded with stars. Your morning routine would still feel like morning. The sunrise would still paint the eastern horizon with colours, reds and oranges and pinks as the light passes through more atmosphere near the horizon. But something would be different. Can you guess what? Actually try to imagine it. Really try. Picture waking up tomorrow and the sun has dimmed by 1%. You walk outside, the light feels maybe slightly less intense, but you can't be sure. Maybe it's just your imagination. Maybe it's cloud cover. Maybe the sun is just lower in the sky than you thought. You check the weather app on your phone, clear skies. You look up. The sun is there, bright as ever, to your eyes. A brightness meter would show the difference, measuring 1,347 watts per square meter instead of 1,361. But to your naked eye, you probably wouldn't know. And that's what makes this scenario so unsettling. The catastrophe would already be beginning, and you might not even notice it happening. That 1% reduction in energy reaching Earth means the planet starts to cool. Not dramatically, not overnight, but measurably, inexorably, like a bank account slowly losing more than it gains. Earth's climate system is extraordinarily complex, with thermal inertia in the oceans that slow temperature changes. The oceans contain an enormous amount of heat, about 1,000 times more heat capacity than the atmosphere. They act as a buffer, absorbing heat when the sun is strong, releasing it when conditions cool. But over months and years, even the oceans can't compensate for a persistent energy deficit. Earth's average temperature, which fluctuates naturally by fractions of a degree from year to year due to ocean cycles like El Niño and La Niña, volcanic eruptions putting aerosols in the atmosphere, variations in Earth's orbit and axial tilt, would begin a steady, measurable decline. Climate scientists would detect it in their data. Global average temperature dropping 0.1 degrees Celsius one year, another 0.1 degrees Celsius the next, then 0.15 degrees Celsius. The trend would be clear. Over a decade, that 1% reduction in solar output would lower Earth's average temperature by about 1 to 1.5 degrees Celsius. From our current average of roughly 15 degrees Celsius down to perhaps 13.5 or 14 degrees Celsius. Now you might be thinking, so what, a degree or two colder? I'll just wear a sweater. Turn up the heat. Problem solved. But you'd be catastrophically wrong, because Earth's climate system is not a simple thermostat that you can adjust up or down independently. It's a complex, interconnected web of feedback loops, tipping points, and nonlinear responses. Systems that look stable can cross invisible thresholds and suddenly reorganize into completely different states. A global temperature drop of 1 to 1.5 degrees Celsius would be the reverse of the global warming we've been experiencing and trying to mitigate. It would push us towards conditions not seen since the Little Ice Age of roughly 1300 to 1850, with the coldest period between 1645 and 1715. During the Little Ice Age, which was caused by a combination of reduced solar activity during the Maunder minimum, when sunspots nearly disappeared, increased volcanic eruptions putting ash and sulfur dioxide into the stratosphere, blocking sunlight, and possibly changes in ocean circulation patterns, global temperatures dropped by about 0.5 to 1 degree Celsius. Just that, half a degree to 1 degree Celsius. And that was enough to cause widespread crop failures across Europe, famines that killed hundreds of thousands, if not millions, rivers freezing that normally stayed liquid year-round, glaciers advancing in the Alps and Scandinavia, growing seasons shortening by weeks, wine grapes failing in regions where they'd grown for centuries, and societies struggling to adapt to the changing conditions. The Thames River in London froze solid enough to hold frost fairs, where people could walk, skate, set up market stalls, roast meat, and hold festivals on the ice. This happened multiple times between the 1400s and the early 1800s. The last frost fair was in 1814. It hasn't happened since because the river doesn't get cold enough anymore, partly due to climate warming, partly due to changes in London Bridge that altered water flow. But during the Little Ice Age, it froze regularly. Paintings from the period show people living and celebrating on what should have been flowing water. In the Netherlands, canals froze solid. In North America, records describe exceptionally harsh winters with snow in places that rarely saw it. So a 1 to 1.5 degrees Celsius drop from a 1% dimming of the sun would push us back toward those conditions, potentially worse, because this cooling would be driven by a persistent reduction in solar input, not temporary volcanic effects or solar cycles. Growing seasons would shorten across the Northern Hemisphere where most of Earth's agricultural land exists. Canada, Russia, Northern Europe, the Northern United States, these regions would see their already relatively short summers become even shorter. Spring would arrive later. Fall would come earlier. The frost-free period when crops can grow would shrink. Crops that currently barely make it to harvest before frost would fail. Wheat, barley, potatoes, crops adapted to cool climates but still requiring a minimum growing season, would face frost that came too early in the fall or lasted too late in the spring. Agricultural yields would drop, not catastrophically at first, maybe 5% to 10% in the first few years, but that matters enormously when you're feeding nearly 8 billion people. Global grain reserves, the stockpiles nations maintain as buffers against bad harvests, typically cover only about 2 to 3 months of global consumption. A 10% drop in global production, sustained over multiple years, would exhaust those reserves rapidly. Food prices would spike. Nations would restrict exports to preserve food for their own populations. Marginal farmland, places where farming is already difficult due to short growing seasons or poor soil, would become economically unviable or physically impossible. Weather patterns would shift in unpredictable ways. The jet streams, those fast-moving rivers of air in the upper atmosphere that govern weather patterns in the mid-latitudes, are driven by the temperature difference between the equator and the poles. The equator receives more direct sunlight. The poles receive angled, weaker sunlight. That temperature gradient drives atmospheric circulation. Reduce the overall solar input and you change the gradient. The jet streams might shift northward or southward. They might weaken or develop more pronounced waves. Weather systems that historically tracked in predictable patterns might shift to new paths. Some regions that rely on predictable rainfall patterns might see those patterns change. Too much rain, too little, rain at the wrong time of year when crops can't use it. Monsoons, seasonal wind patterns that bring life-giving rains to billions of people in Asia, depend on differential heating between ocean and land. In summer, the land heats faster than the ocean, creating low pressure over the land that draws in moist ocean air. That air rises, cools, and releases its moisture as torrential rain. It's a predictable cycle that has sustained civilizations in India, Southeast Asia, and East Asia for thousands of years. But change the temperatures, change the heating rates, and the monsoons might weaken, shift, or fail. Regions that depend on monsoon rains for their water supply and their agriculture would face droughts even if global temperature only dropped by a degree or two. Ocean currents that distribute heat around the planet, massive conveyor belts of water driven by temperature and salinity differences, might slow or shift. The Gulf Stream, technically the North Atlantic Current, carries warm water from the Caribbean along the eastern coast of North America and across the Atlantic to Europe. That's why Western Europe, despite being at the same latitude as Canada, has such a relatively mild climate. London sits at about 51.5 degrees north latitude, roughly the same as Calgary, Canada, which is at 51 degrees north. But London's average winter temperature is around 4 to 5 degrees Celsius, while Calgary's is around -7 to -9 degrees Celsius. The difference is the Gulf Stream warming Europe. But the Gulf Stream is driven by a delicate balance. Warm, salty water from the tropics flows north, cools as it moves into higher latitudes, becomes denser because cold water is denser than warm water, and salty water is denser than fresh water, sinks in the North Atlantic near Greenland and Iceland, and flows back south at depth, completing a massive circulation loop called the Atlantic Meridional Overturning Circulation. Change the temperatures, change the salinity through melting ice or changing rainfall patterns, and this circulation weakens or stops. Without the Gulf Stream, Western Europe would have a climate similar to Canada at the same latitude. Harsh winters, short summers, difficult agriculture. The tens of millions of people living in Britain, France, the Netherlands, Germany, Scandinavia, they would face Arctic-like conditions, and this is just from 1%, a barely perceptible dimming that you probably couldn't detect with your eyes. It would look the same, you could still get a sunburn if you stayed out too long. Plants would still photosynthesize, though perhaps slightly less efficiently, with 1% less light. Animals would still be active, but the global system would fall under stress. Food production would decline. Some species adapted to warm climates would struggle at the margins of their ranges. Ice would persist longer at higher latitudes, reflecting more sunlight back to space, which would accelerate the cooling in a feedback loop we'll discuss in more detail later. Sea ice in the Arctic and Antarctic would extend farther from the poles in winter and retreat less in summer. Can you visualize this? Can you really see it in your mind? A world only slightly colder, but with agriculture failing in many regions, weather patterns shifting, millions or billions of people facing food insecurity, nations competing for shrinking resources, climate refugees migrating towards still habitable zones. Or does your brain struggle with it because the change seems too small to matter? That's the insidious nature of this scenario. The changes start small, almost unnoticeable, but they cascade, they amplify, they trigger responses in complex systems that magnify the initial change into catastrophic outcomes. And we're still only talking about 1%, just 1%. It remains 99% as bright as normal. But Earth is already sliding toward crisis. Now imagine what happens when the dimming continues. But we're not stopping at 1%. Because in this scenario, the sun doesn't just dim a little and stabilize. It keeps going, it keeps fading. So let's say it loses 5% of its brightness. 5%. Now we're in serious trouble. Try to imagine this. Really put yourself there. The sun still looks bright in the sky, still too bright to look at directly without hurting your eyes, but it's putting out 5% less energy. That might not sound like much. After all, what's 5%? It's 1/20th, barely noticeable in most contexts of daily life. A 5% discount at a store, a 5% pay cut. Annoying but manageable, right? But remember what we're dealing with. That's 5% of 174 petawatts, That's about 8.7 petawatts less energy reaching Earth every second. For comparison, that's more than 400 times all the energy human civilization uses. Can you wrap your mind around that? Think of every power plant on Earth, every solar panel soaking up sunlight and converting it to electricity, every wind turbine spinning in the breeze, every coal-fired power plant burning millions of tons of coal, every nuclear reactor splitting uranium atoms, every hydroelectric dam channeling falling water through turbines, every natural gas plant, every geothermal facility. All of them combined produce maybe 20 terawatts of power, though most energy is actually used as direct heat or motion, not converted to electricity. The sun's 5% dimming removes 8,700 terawatts from Earth's energy budget. You're not imagining this at the right scale yet, are you? Let me help you. Imagine if every power plant on Earth shut down simultaneously and stayed off forever. That would prove catastrophic for modern civilization. Most cities would go dark. Hospitals would lose power. Water treatment plants would stop. Food refrigeration would fail. Transportation would halt as electric trains stopped and fuel pumps couldn't operate. Communication networks would collapse. Within days, modern civilization would descend into chaos. Now multiply that catastrophe by 400. That's what a 5% solar dimming represents in energy terms. It's not just losing our power plants, it's losing 400 times that amount of energy from the total system that keeps Earth habitable. A 5% reduction in solar output would lower Earth's average temperature by about 5 to 7 degrees Celsius over a period of years or decades, depending on how quickly the dimming occurred and how fast Earth's climate system could respond. From 15 degrees Celsius down to perhaps just 8 to 10 degrees Celsius. Think about what that means globally. The global average temperature during the last major ice age, the last glacial maximum about 20,000 years ago, was only about 5 to 6 degrees Celsius cooler than today. That's it, just 5 to 6 degrees Celsius cooler. Ice sheets called the Laurentide ice sheet covered Canada and extended south into what's now the northern United States, reaching as far south as New York City, burying it under ice. The Fennoscandian ice sheet covered Scandinavia and extended into northern Europe. These ice sheets were kilometers thick, massive enough that their weight depressed the continental crust, pushing it down into the mantle beneath. The ice locked up so much water that global sea levels dropped by about 120 to 130 meters. That's 390 to 425 feet. Shorelines extended far beyond where they are today. Land bridges existed that allowed humans and animals to migrate between continents. The Bering Land Bridge connected Asia to North America across what's now the Bering Strait, allowing the first humans to enter the Americas. Britain was connected to mainland Europe because the North Sea was dry land. Indonesia was connected to mainland Asia. A 5% dimming of the sun would push us into ice age conditions, but it would happen faster than any natural ice age in Earth's history. Because the sun dimming is a faster process than the gradual orbital changes, the Milankovitch cycles that normally trigger ice ages over thousands of years. Glaciers would begin advancing from the poles and from mountain ranges, not slowly over millennia, but visibly over decades. You could measure their progress year by year. Scientists could watch them extending, consuming land, burying ecosystems. Snow would persist year-round at latitudes where it currently melts every spring. Northern Canada, Alaska, Scandinavia, Russia, Scotland, these regions would see permanent snow cover. The snow would accumulate, compact into ice, build into glaciers that would flow slowly outward under their own weight. Growing seasons in temperate regions would collapse. Places like the northern United States, southern Canada, northern Europe, regions that currently produce enormous amounts of food for global markets, would see their agricultural capacity plummet. Crops that feed billions of people, wheat, corn, rice, soybeans, would fail across vast areas. Wheat grows best at temperatures between 15 and 25 degrees Celsius during its growing season. Drop global temperatures by 5 to 7 degrees Celsius and most current wheat-growing regions become too cold. The wheat belt in the Great Plains of North America, the grain fields of Ukraine and southern Russia, the wheat farms of Australia, all would face temperatures too cold for reliable crops. Corn requires even warmer temperatures, typically 18 to 27 degrees Celsius, and a long frost-free growing season of 120 to 180 days depending on the variety. Drop temperatures and shorten the growing season and corn production collapses. Rice needs warm temperatures, 20 to 35 degrees Celsius, and abundant water, typically grown in flooded paddies. Rice feeds more than half of the global population, especially in Asia. If temperatures drop and monsoon patterns shift, rice production fails. Billions of people depend on rice as their primary calorie source. What do they eat when the rice paddies freeze or dry up? There would be no backup, no alternative. The global food system, which is already stretched thin with limited reserves, would face simultaneous failures across multiple growing regions of different staple crops. You can't just shift agriculture to new regions quickly. Soil takes thousands of years to develop. Infrastructure, farms, irrigation systems, roads, storage facilities, processing plants, all of that exists where it exists because that's where agriculture has been practiced historically. You can't just move it all toward the equator in a few years. Billions of people in regions that became too cold for farming would need to migrate. But migrate where? The equatorial regions, while warmer than the poles, would also be affected. Even if the equator remained warm enough for some agriculture, maybe 15 to 20 degrees Celsius, the climate patterns those regions depend on would be disrupted. Monsoons that deliver water to India, Southeast Asia, parts of Africa, these are driven by temperature differentials between ocean and land between equator and poles. Change those differentials and the monsoons change. They might weaken dramatically, shift to different regions, or fail entirely. Regions that depend on monsoon rains for their water supply and their agriculture, supporting perhaps 2 to 3 billion people, would face drought even if the temperature remained tolerable. The Amazon rainforest, the largest tropical rainforest on Earth, which depends on specific temperature and rainfall patterns to maintain itself, would begin to die back. The Amazon is not just important locally for Brazil and neighbouring countries, it's a global climate regulator. The trees absorb enormous amounts of carbon dioxide through photosynthesis, perhaps 2 billion tonnes per year, acting as a carbon sink that removes CO2 from the atmosphere. They release oxygen, contributing a significant fraction of global oxygen production, though the exact percentage is debated, and much of the oxygen is consumed by decomposition in the forest itself. They release water vapour through transpiration, pulling water from the soil and evaporating it from leaf surfaces. That water vapour forms clouds that reflect sunlight and produce rain, creating a self-sustaining cycle. The forest creates its own weather to some extent. If the Amazon dies, those regulatory effects vanish. More CO2 accumulates in the atmosphere. Less oxygen is produced, though this is less critical since the ocean's phytoplankton produce most of Earth's oxygen. Less rain falls in the region, accelerating the dieback in a feedback loop. The Amazon transitions from rainforest to savanna or even desert. The indigenous people who live there, the species that depend on it, the global climate patterns it influences, all disrupted. And this is just one ecosystem. Tropical rainforests in the Congo Basin, in Southeast Asia, in Central America, all would face similar pressures as temperatures dropped and rainfall patterns shifted. Ocean temperatures would drop. The ocean surface layer, which mixes with the atmosphere and responds relatively quickly to changes in air temperature, would cool first. Fish populations, which are adapted to specific temperature ranges with different species tolerating different temperatures, would shift toward the equator, trying to stay in water that matches their thermal tolerances. Commercial fisheries in temperate and polar regions would collapse as the fish they depend on moved away or died. Cod, herring, salmon, pollock, all the species that sustain fishing industries and provide protein for millions of people, would shift their ranges or decline in numbers. Coral reefs, already stressed by warming in our current timeline, would face a different but equally deadly crisis as cooler waters change the chemistry and the light levels they depend on. Corals are animals, but they live in partnership with single-celled algae called zooxanthellae that live inside their tissues and photosynthesize, providing the coral with up to 90% of its energy needs. The coral provides the algae with a protected environment and nutrients. It's a delicate partnership that only works within specific temperature ranges, typically 20 to 30 degrees Celsius. Drop the temperature too much or reduce light levels and the partnership breaks down. The algae are expelled or die. The coral bleaches, losing its colours, which comes from the algae. Without the energy from photosynthesis, the coral slowly starves and dies. Coral reef ecosystems, which support about 25% of all marine species despite covering less than 1% of the ocean floor, would collapse. The fish, crustaceans, mollusks, echinoderms, sponges, all the biodiversity that depends on the reef structure for food and shelter, would lose their habitat. The loss would cascade through marine food webs. And remember, this is happening while the global human population is also in crisis, facing food shortages, mass migration, resource competition. The oceans can't serve as a fallback food source because they're collapsing too, and we're still only talking about 5% dimming. It would still be 95% as bright as normal. You could still go outside on a sunny day and feel warmth on your face. It would be noticeably less intense than you remember. You could still see your shadow moving across the ground as the day progressed, though it might be slightly less distinct. Birds would still fly, trees would still grow, though slower. The sun would still rise in the east and set in the west. The earth would still orbit, still rotate, still experience day and night. But the world would be dying. Human civilization, which has existed for perhaps 10,000 years in its agricultural form and only a few hundred years in its industrial form, all of it built on the assumption of stable climate and reliable food production, would face catastrophic disruption. Try to imagine the chaos. Really try. Can you picture 2 or 3 billion climate refugees trying to migrate toward habitable zones? The equatorial regions, the only places still warm enough for agriculture, would be overwhelmed with more people than they could possibly support. Competition for resources would become violent. Nations would close borders, militarize them, use force to turn back refugees. Wars would break out over arable land, over water resources, over the remaining productive regions, and this would all be happening while the sun continued to dim, while the cold continued to advance, while growing seasons continued to shrink with each passing year. The infrastructure we depend on would begin to fail. Power grids in cold regions would be strained beyond capacity as people tried desperately to heat their homes against the worsening cold, but power plants themselves depend on cooling water, often drawn from rivers. If those rivers freeze, the plants can't operate, they shut down. The grid fails, people freeze in their homes. Transportation networks would be disrupted by advancing ice and snow. Roads would become impassable, buried under meters of snow that never melts. Railways would be blocked. Airports would shut down as runways ice over and visibility drops in constant snowstorms. The global supply chains that modern civilization depends on, the just-in-time delivery of goods, the international trade in food and materials, would fracture and collapse. You can't ship food from where it's grown to where it's needed if the ships can't navigate ice-choked seas and the trucks can't drive on frozen roads. Manufacturing would halt as factories lost power and couldn't get raw materials. Hospitals would struggle to function without reliable electricity, heat and medicine supplies. Water treatment plants would freeze and fail, forcing people to boil water or risk disease. Communication networks, cell towers and internet infrastructure would degrade as maintenance became impossible in frozen regions and power became unreliable. The complex web of technological systems that support modern life would unravel, and billions of people would attempt to survive in conditions their ancestors might have managed with pre-industrial lifestyles, but which modern people are completely unprepared for. The death toll would prove staggering. Conservative estimates might suggest billions dead within the first decade or two. From cold, yes, but mostly from starvation as food production collapsed. From disease as sanitation systems failed and populations were crowded into shrinking habitable zones. From violence as people fought over scarce resources, from the breakdown of medical care, from the 1,000 cascading failures that follow when complex systems collapse. And this is all happening in a scenario where the sun has only dimmed by 5%. Only 5%. The sun is still more than 90% as bright as it should be. And Earth is already in crisis. Billions dying, ecosystems collapsing, civilization fracturing into desperate isolated communities fighting for survival. Can you even imagine it? Can you really picture what that world would look like? Try. Close your eyes and try to imagine a world where everything north of the 40th parallel, roughly the latitude of Philadelphia, Madrid or Beijing, is frozen solid. Covered in advancing ice, empty of human habitation, and the narrow band of surviving civilization clustered around the equator is overcrowded, starving, desperate, watching the ice approach year by year. Can you see it? Or does your mind refuse to go there because it's too far from your experience, too alien to everything you know? That's okay, that's normal. The human brain didn't evolve to imagine global apocalypse. We evolved to deal with immediate local threats. A predator in the bushes, a storm approaching, a rival group, not the slow death of an entire planet. But I'm going to keep pushing you to try, because we're not done. The sun keeps dimming. It's not finished. It loses 10% of its brightness. A full 10%. 1/10 of its normal energy output, gone. Earth's average temperature would drop by perhaps 10 to 12 degrees Celsius over the years following this additional dimming. From our normal 15 degrees Celsius down to maybe 3 to 5 degrees Celsius. That's 37 to 41 degrees Fahrenheit for the global average. For reference, that's colder than the average annual temperature in London today, which is about 11 degrees Celsius, or Seattle at 10 degrees Celsius, or Paris at 12 degrees Celsius. Except that's the global average we're talking about. The average across all latitudes, all seasons. Picture this if you can. Actually stop and try. The global average means some places are colder, some warmer. The equator, the warmest zone on Earth, might be at 10 to 12 degrees Celsius. Cool but not freezing, like a typical autumn day in a temperate climate. The poles? Try minus 70 degrees Celsius or minus 80 degrees Celsius or even colder. Temperatures that would freeze exposed skin in minutes, where the air itself feels like it's burning your lungs when you breathe. Can you visualize what a world at those temperatures looks like? your mind probably can't quite get there, can it? Because you've never experienced it. You've experienced cold winters. Maybe you've been to Alaska or northern Canada or Scandinavia in January. Maybe you've felt minus 20 degrees Celsius or minus 30 degrees Celsius and thought it was bitterly cold. But imagining the entire planet locked in those temperatures or colder year-round with no warm season coming, no spring, no summer, just endless cold getting worse every year. That requires a mental leap your brain resists. The northern United States would resemble Antarctica is today. Think about that. Really think about it. New York City, with its 8 million people, its skyscrapers, its culture and history. Chicago, the hub of the Midwest. Seattle, Portland, Boston, Minneapolis, Detroit. All these cities and the millions who live in them and the surrounding regions, they would have the same climate as McMurdo Station in Antarctica has today. Permanent ice, temperatures that regularly drop below minus 40 degrees Celsius in winter, which is the same in both Celsius and Fahrenheit, interestingly. At minus 40 degrees Celsius, exposed skin freezes in minutes. Metal becomes brittle, plastic shatters, rubber becomes hard as rock. No trees would grow there. Trees need a growing season, a period of warmth where they can photosynthesize and produce the sugars needed for growth and maintenance. Drop below a certain threshold and photosynthesis can't happen efficiently enough. The tree uses more energy maintaining its metabolism than it can produce. It dies. No plants would survive except perhaps some lichens and mosses adapted to extreme cold, huddled in microhabitats where a rock provides a few degrees of extra warmth. No animals except perhaps a few adapted species near the coasts where the frozen ocean might moderate temperatures slightly. We're talking minus 30 degrees Celsius instead of minus 50 degrees Celsius. Still utterly lethal to humans without heavy protection and artificial heat. Canada, Scandinavia, Russia, Northern Europe, all of these vast regions spanning millions of square kilometers, supporting hundreds of millions of people in our current world, would experience conditions similar to the Antarctic interior today, which is one of the most hostile environments on Earth. The Soviet Union's Vostok station in Antarctica recorded the lowest temperature ever measured on Earth's surface, minus 89.2 degrees Celsius in July 1983. Imagine entire continents at those temperatures. Permanent snow and ice accumulating year after year with no melting season. Glaciers hundreds of meters thick in the first decades, growing to kilometers thick over centuries, the weight compressing the snow into dense ice, the ice flowing slowly outward under its own mass. No growing season, not in summer because there is no summer. It might be above the horizon for part of the year at high latitudes due to Earth's axial tilt, but it's so weak, dim, providing only 90% of its normal pathetic output at those latitudes where the angle is already shallow, that it can't warm anything. The ground stays frozen solid. Permafrost extends deep into the earth. You physically could not survive there without artificial heat, without sealed environments, without constant energy input to maintain livable temperatures inside while the outside world is a frozen hell. Think about what that means practically. Where do hundreds of millions of people go? How do they migrate when most of Earth is becoming uninhabitable? The equatorial regions would be Earth's last refuge, the only zone still warm enough for any kind of normal life. But even there, temperatures would be what we consider cool temperate today, maybe 8 to 12 degrees Celsius at the warmest on the equator, colder as you move north or south. That's the temperature of a mild spring or fall day in the current temperate zones. Comfortable with a light jacket, but this would become the warmest the planet gets anywhere, year-round. The tropics, currently hot and humid, would be cool. The subtropics, currently warm, would be cold, and billions of people from the now uninhabitable northern and southern latitudes would attempt to crowd into this shrinking habitable zone. But here's the cruel paradox. Even if the equator remained at 10 or 12 degrees Celsius, even if it was technically warm enough for human survival, it couldn't support anywhere near the global population. Agriculture would be possible, barely, but yields would be a fraction of what they are today with full sunlight and warmer temperatures. You might be able to grow some crops, cold-adapted varieties, but the growing season would be short and the yields low. The equatorial zone, even if it stretched from 30 degrees south to 30 degrees north latitude, couldn't possibly grow enough food for 8 billion people, or even a fraction of that. Most people would starve. Simple as that. Food production, even in the equatorial regions, would be severely limited. Photosynthesis, the process that plants use to convert sunlight, carbon dioxide and water into sugars and oxygen, would be dramatically less efficient with only 90% of normal sunlight. Plant growth rates depend directly on light intensity up to a saturation point. Reduce the light and you reduce growth. It's a nearly linear relationship for many crops in their normal light ranges. A 10% reduction in light means roughly a 10% reduction in photosynthesis rates, which means slower growth, lower yields, less food produced per hectare per year. Some crops might still grow slow and stunted, producing less. Other crops, those adapted to bright sunlight, wouldn't grow at all because they couldn't gather enough energy to complete their life cycles before the shortened growing season ended. Remember, growing seasons would be shortened too because even the equator would have cooler temperatures. Frost might occur at higher elevations even in the tropics. Rain patterns would shift unpredictably. Some areas might get more rain, others might become desert. The monsoons utterly disrupted. The predictable patterns that farmers have relied on for thousands of years, gone, replaced with chaos and uncertainty. But plants aren't the only problem. The entire climate system would be fundamentally different. Weather patterns would be unrecognizable compared to what we know today. The jet streams that govern weather in the mid-latitudes would weaken dramatically or shift entirely. These are bands of fast-moving air high in the atmosphere, typically at altitudes of 9 to 12 kilometers, driven by temperature differences between the equator and the poles. The equator heats more than the poles, creating a temperature gradient. That gradient drives atmospheric circulation. Warm air rises at the equator, flows toward the poles at high altitude, sinks in the subtropics, and flows back toward the equator near the surface, creating circulation cells. The jet streams form at the boundaries between these cells where temperature gradients are steep. They meander north and south, creating the storm tracks and weather patterns we're familiar with. But reduce the overall temperature, change the gradient between equator and poles, and the jet streams weaken, shift, or behave erratically. That changes everything about how weather behaves. Storm tracks shift. Rainfall patterns change. Some regions that currently get predictable rain might become dry. Others might get flooded. Agricultural planning becomes impossible when you can't predict whether you'll have rain when you need it. Monsoons, which billions of people in Asia depend on for water and agriculture, would fail. Monsoons are driven by the temperature difference between the ocean and the land heating at different rates. In summer, the land heats faster, creating low pressure over the continent that draws in moist ocean air. That moist air is forced to rise by the topography, mountains, highlands. As it rises, it cools. Cooler air can't hold as much water vapor, so the moisture condenses and falls as torrential rain. It's a predictable cycle, the summer monsoon that has sustained rice cultivation and civilization in India, Bangladesh, Myanmar, Thailand, Vietnam, Cambodia, Laos, southern China for thousands of years. But change the temperatures, reduce the heating, and the cycle breaks. The land might not heat enough to create strong low pressure. The pressure differential between ocean and land might not form. The moist ocean air might not be drawn in, or might not rise enough, or might not cool enough to release its moisture. The rains might not come. India, with its population of 1.4 billion people, Bangladesh with 170 million, all of Southeast Asia, all dependent on monsoon rains, would face catastrophic drought even if temperatures remain tolerable. Where do over 1 billion people get water when the monsoons fail? When the rivers fed by monsoon rains dry up? When the groundwater, recharged by monsoon rain seeping into the soil, depletes and wells run dry? Ocean currents that distribute heat around the planet, the great conveyor belts of warm and cold water that moderate regional climates, would slow or stop entirely. The Gulf Stream, which we mentioned earlier, carries warm water from the Caribbean up along the eastern coast of North America and across the Atlantic to northern Europe. It's part of a larger circulation called the Atlantic Meridional Overturning Circulation, AMOC for short. This circulation is driven by density differences in seawater. Warm, salty water from the tropics flows north. As it moves into higher latitudes, it cools. Cold water is denser than warm water. The water sinks in the North Atlantic, particularly in areas near Greenland and Iceland, and flows back south at depth, completing the loop. This circulation, this overturning, transports an enormous amount of heat northward, perhaps 1.3 petawatts of heat energy, warming northwestern Europe significantly. Without it, the climate there would be much colder, more similar to Siberia or northern Canada at similar latitudes. But this circulation is sensitive to temperature and salinity changes. Cool the surface waters too much, or change the salinity through melting ice, adding fresh water or changing precipitation patterns, and the density-driven sinking weakens or stops. The Gulf Stream slows or shuts down. Europe loses its heat source. Western Europe plunges into Arctic conditions. Britain, at 50 to 60 degrees north latitude, would experience winters like northern Canada or Siberia today. Temperatures of -30 to -40 degrees Celsius or colder. The tens of millions of people in the UK would face conditions utterly incompatible with the infrastructure and society they have. Central heating systems designed for mild winters would be overwhelmed. Buildings not insulated for extreme cold would become uninhabitable. Agriculture would become impossible. The British Isles would need to be evacuated, but evacuated to where? Northern France, northern Germany, Scandinavia, all in the same situation. The only escape would lie south toward the Mediterranean, which itself would be cold, perhaps barely above freezing in winter, or toward the equator thousands of kilometers away. This pattern repeats globally. Japan, warmed by the Kuroshio Current, the Pacific equivalent of the Gulf Stream, would lose that warming and freeze. Eastern North America, also influenced by the Gulf Stream, would become colder. The entire global pattern of ocean heat distribution would collapse and regional climates would reorganize around new, colder norms. And the oceans themselves would begin to freeze, not everywhere. The ocean is deep, averaging about 3.7 kilometers globally. The deepest parts, like the Mariana Trench at nearly 11 kilometers, are far too deep and under too much pressure to freeze. And there's geothermal heat from Earth's interior leaking up through the ocean floor at spreading ridges and volcanic hotspots. But the surface, especially at higher latitudes, would freeze solid. Try to picture this in your mind. Actually try. The Atlantic Ocean freezing, the Pacific Ocean freezing, not just near the poles where we expect ice, but extending toward the equator. Ice sheets kilometers thick forming on top of what was once open water. Ships trapped and crushed by the pressure of the ice closing in around them. ports abandoned as the harbours ice over, entire coastlines buried under advancing ice. Can you see it? Or does your brain refuse to construct that image because it's too alien to everything you know about Earth? The Southern Ocean around Antarctica would freeze far north of where it currently does, perhaps reaching the latitudes of southern Australia or the southern tip of South America. The Arctic ice cap would extend well into the Atlantic and Pacific, covering waters as far south as Scotland, Iceland fully encased in ice year-round, southern Alaska, the Aleutian Islands, all frozen solid. And remember the albedo feedback we discussed earlier. Albedo is a measure of how much light a surface reflects. Fresh snow has an albedo of about 0.8 to 0.9, meaning it reflects 80% to 90% of the sunlight that hits it, absorbing only 10% to 20%. Dark ocean water has an albedo of about 0.06, reflecting only 6% and absorbing 94% of the sunlight, converting it to heat. When the planet is warm and ice-free, ocean water absorbs sunlight and warms, which helps maintain mild temperatures. When the planet cools and ice forms, that ice reflects sunlight back into space. The more ice forms, the more sunlight is reflected, which means less heat absorbed by the planet, which means colder temperatures, which means even more ice forms. Do you see the feedback loop? Do you understand how it accelerates the cooling beyond what the 10% dimming alone would cause? This is what makes the situation so catastrophically dangerous. The direct cooling from reduced sunlight is bad enough, pulling Earth toward Ice Age conditions, but that cooling triggers cascading effects that make everything worse. More ice means higher albedo. Higher albedo means more reflection. More reflection means less absorbed heat. Less absorbed heat means lower temperatures. Lower temperatures mean more ice. Round and round, spiralling downward into a frozen state that's incredibly difficult to escape even if our star's output later recovered. This is one of the nightmare scenarios climate scientists worry about in the context of climate change, though in reverse. Not a cooling feedback loop, but a warming one. But the physics is the same. Small changes can trigger feedbacks that lock the system into a new stable state far from the original. This is why 10% dimming is not just 10% worse than 5% dimming. It's catastrophically worse because it crosses thresholds that trigger runaway feedbacks. At 10% dimming, with global temperatures perhaps 10 to 12 degrees Celsius below normal, Earth is locked into an ice age far more severe than any in human history. The ice extends from the poles toward the equator. The oceans freeze over vast areas. The albedo skyrockets. The planet reflects more and more sunlight. The cooling accelerates. And even if we could somehow restart the sun to full brightness instantly, the planet might stay frozen for centuries or millennia because of the ice already present and the feedback loops maintaining the cold state. This is the terrifying nature of climate tipping points. They're easy to cross but incredibly hard to reverse. At this stage, perhaps 2 or 3 decades into the dimming, if it's occurring gradually, most of Earth's human population would be dead. Not from the cold directly, though many would freeze, especially as infrastructure failed and people couldn't maintain heat in their homes, but from starvation as global agriculture collapsed, from disease as sanitation systems failed and populations crowded into the shrinking habitable zones, spreading pathogens rapidly through dense populations with limited medical care, from violence as people fought over the remaining resources, over food, over shelter, over any warm place, from the breakdown of medical care as hospitals lost power and medicine supplies and trained staff, from the 1,000 cascading failures that follow when complex systems collapse. Maybe 1 billion people would survive, maybe less. Clustered in the equatorial regions, scraping out an existence, watching the ice advance year by year. Knowing that the cold was coming for them too, that the habitable zone was shrinking, that eventually there would be nowhere left to go. And we're only at 10% dimming. It would still appear brilliant in the sky to anyone who could still see it through the cloud cover and the blowing snow. You could still see it rise and set. It would still hurt your eyes if you stared at it. Days and nights would still happen on the normal 24-hour cycle. Earth would still orbit the Sun every 365.25 days. Nothing about the mechanics of the solar system would have changed. Just the energy output of the star at the center. Just 10% less energy. And Earth would be a frozen wasteland where most life had died, and the survivors were desperately, hopelessly trying to cling to existence in a shrinking refuge that would eventually freeze too. Now let's go to 25%. The Sun loses a quarter of its brightness. 3/4 of its normal output remains. Earth's average temperature would plummet to perhaps -10 to -15 degrees Celsius. That's 14 to 5 degrees Fahrenheit. For context, that's colder than the average temperature in Antarctica at the coast today, which is about -10 degrees Celsius, and approaching the average temperature in the Antarctic interior, which is about -57 degrees Celsius depending on location. But we're talking about the global average. Everywhere on Earth averaging -10 to -15 degrees Celsius. The equator might be at freezing or just above, maybe 0 to 2 degrees Celsius. The poles would be unimaginably cold, perhaps -100 degrees Celsius or colder. The oceans would freeze extensively. We're not talking about a thin layer of ice. We're talking about ice hundreds of meters thick, perhaps kilometers in some regions, covering vast areas of the ocean surface. Not solid all the way through, the ocean is too deep for that, averaging 3.7 kilometers and reaching nearly 11 kilometers in the deepest trenches. And there's still some geothermal heat from Earth's interior warming the deepest waters through volcanic activity at mid-ocean ridges and hotspots. But vast areas of the ocean surface would be covered in thick, permanent ice. The Arctic and Antarctic ice caps would extend until they nearly met at the equator. You could potentially walk from the North Pole to the South Pole across the ice. Only a narrow band of open water would remain in the tropics, perhaps between 10 degrees north and 10 degrees south latitude, and that water would be cold, near freezing, perhaps 0 to 2 degrees Celsius. Marine life would be utterly devastated. Most fish species are ectothermic, meaning their body temperature matches their environment. They're adapted to specific temperature ranges. Each species has an optimal temperature range where their metabolism functions efficiently, where they can hunt, digest food, reproduce. Push them outside that range and their metabolism slows. They become sluggish, they can't catch prey, they can't escape predators, they can't reproduce successfully, they die. Coral reefs, those incredible ecosystems supporting 25% of all marine species, would be long dead by this point. They died back when temperatures first dropped below their tolerance range, probably during the 5% or 10% dimming phase. Now the ocean where they once existed is covered in ice. Kelp forests, those towering underwater forests of brown algae that provide habitat for countless species in temperate coastal waters, dead, frozen. The vast majority of marine ecosystems would have collapsed entirely by this point. Some deep ocean life might survive, clustered around hydrothermal vents, where Earth's internal heat seeps out of the crust and creates oases of warmth in the frozen deep. These vents spew superheated water, perhaps 300 to 400 degrees Celsius, loaded with minerals and chemicals. Specialized bacteria and archaea derive energy from the chemicals rather than from sunlight, forming the base of a food chain that includes giant tube worms, crabs, shrimp, fish, all adapted to extreme conditions. These vent communities might persist even as the rest of the ocean freezes, but they would be isolated islands of life in a dead sea, and even they would fall under pressure as the ice above thickens and the cold penetrates deeper into the ocean. How long can they survive? Decades? Centuries? Eventually, perhaps, even they would succumb, but for now, they might be the last complex ecosystems on Earth. Everything else dead. On land, the situation would be even more catastrophic. With only 75% of normal sunlight, photosynthesis would be severely limited. Even at the equator, even in full daylight, plants would struggle to gather enough energy to survive. Most plant species would be dead. Think about what that means globally. No forests, no grasslands, no shrublands. The biomes that cover the continents all gone. Trees would die as they exhausted their energy reserves stored in trunks and roots, unable to photosynthesize enough to replenish them. It takes energy to maintain metabolism, to keep cells alive, to repair damage. If a plant can't generate more energy than it uses, it dies. Grasslands would turn brown and die, the grass freezing and shattering like glass in the cold. Any ecosystem that depended on photosynthesis, either directly as a primary producer or indirectly by consuming things that photosynthesize, would collapse. Herbivores would starve as plants died. Carnivores would starve as herbivores died. Decomposers would run out of organic matter to break down. The entire food chain collapsed from the bottom up. The continents would freeze deserts, lifeless expanses of ice and rock under a dim sun. Agriculture would become completely impossible except perhaps in artificially heated greenhouses, with artificial light supplementing the weak sunlight. And even then, you'd need enormous amounts of energy from somewhere to power those lights and heaters. Where would that energy come from? Fossil fuels would still work chemically. The laws of combustion don't depend on the sun. You could still burn coal, oil, natural gas to generate electricity and heat, but you'd be burning through those reserves at an incredible rate, trying to keep a few pockets of humanity alive in a frozen hellscape. A single greenhouse producing enough food for even a small community would require enormous amounts of energy. Heat to keep the interior above freezing so plants can grow. Artificial light to replace the missing sunlight, probably high-intensity LEDs optimized for photosynthesis. Water, which would need to be melted from ice or snow. Air circulation to distribute CO2 to the plants. All of it powered artificially. And those fossil fuel reserves, while large, are not infinite. We've been extracting and burning them for about 150 years in our industrial civilization. And in our current timeline, we're already concerned about reserves running low. In this scenario, where you're burning fuel at vastly higher rates just to survive, producing heat and power on a scale far beyond current consumption, those reserves would be exhausted much faster. Coal might last a few decades, oil and gas maybe less. And then what? When the coal mines are empty and the oil wells are dry and the natural gas fields are depleted, what do you burn? Wood? There are no trees. They're all dead. Biomass? There's no biomass. Everything's frozen. Nuclear power would still work. The sun might be dimming, but uranium is still uranium. Plutonium is still plutonium. Nuclear fission doesn't care about sunlight. The process of splitting heavy atoms into lighter ones and releasing energy from the mass difference, that's governed by the strong nuclear force and Einstein's E=mc². It's independent of the sun. You could theoretically maintain some human outpost powered by nuclear reactors, as we discussed before. Build them underground where the temperature is more stable, insulated by kilometers of rock and soil from the brutal cold of the surface. Use the reactor to generate heat and electricity. Heat the habitat to a livable temperature. Use electricity to grow food hydroponically. plants growing in nutrient-rich water under artificial lights. Recycle air and water in closed systems. It's technically possible. It's been done on a small scale on the International Space Station and in closed biosphere experiments. But here's the fundamental problem with this survival strategy. That's not civilization. That's not human society as we know it. That's a few hundred, or at most a few thousand people living in sealed bunkers, completely dependent on technology that requires constant maintenance, with no connection to the surface, no access to the frozen dead world above. Nuclear reactors are complex machines. They need highly trained operators who understand reactor physics, engineering, safety protocols. They need replacement parts when components wear out, pumps, valves, control rods, sensors, miles of piping. They need fuel, uranium or plutonium, which has to be mined, enriched or processed, fabricated into fuel assemblies. They need cooling systems, typically water-based. And what happens if the cooling water freezes? All of this requires a functioning industrial civilization to support it. You need supply chains. You need factories to manufacture parts. You need mines to extract materials. You need specialists in dozens of fields: metallurgy, electronics, nuclear engineering, materials science, chemistry. All of it requires education systems to train people and knowledge systems to preserve what's been learned. And with most of Earth uninhabitable, with billions dead, with the surface a frozen wasteland, you don't have that industrial base. You have isolated bunkers doing their best to survive with whatever they manage to stockpile before the collapse. And one by one, inevitably, those bunkers would fail. Technology degrades, seals crack, pumps fail, electronics malfunction, radiation leaks occur, and without the ability to manufacture replacements, to import supplies, to call in specialists from other locations, the bunker dies. Maybe it takes a decade, maybe a generation or two if they're very lucky and very skilled. But entropy always wins. Systems degrade. Knowledge is lost when the people who hold it die without successfully passing it on to the next generation. And in an environment where you're struggling just to stay alive, where food is limited and stress is high and the future looks hopeless, how well can you educate the next generation? How much knowledge survives? So at 25% dimming, humanity would be effectively doomed. Not extinct immediately, not all at once, but doomed as a species in the long term. The last survivors might persist for decades, might even persist for a century or two in the absolute best case scenario, with perfectly functioning nuclear bunkers and perfect knowledge transfer and perfect maintenance. But they would live on borrowed time, using up finite resources, unable to expand, unable to rebuild, just waiting for the inevitable failure that would end them. There would be no future, no hope of recovery, no way to return to the surface even if our star miraculously brightened again, because the surface would remain locked in ice that would take thousands of years to melt. They would die. All of them. Eventually. And humanity would go extinct. Earth would be left with only the simplest forms of life, bacteria and archaea clustered in isolated pockets deep in the ocean or deep underground. And the sun, the star that once sustained a thriving biosphere teeming with millions of species, would still be visible in the sky. Dimmer, yes, noticeably weaker if you compared it to your memory of what it used to be, but still bright enough to cast shadows if you stood on the frozen surface at the equator. Still shining, still undergoing fusion in its core, still putting out 75% of what it once did. But not enough. Not enough to maintain the energy balance that life requires. Not enough to keep Earth habitable. Not enough to save us. Let's continue to 50%. Half the sun's normal brightness. This is where things become truly apocalyptic, where even the last remnants of hope disappear. Earth's average temperature would drop to perhaps -40 to -50 degrees Celsius or colder. That's -40 to -58 degrees Fahrenheit. At -40 degrees Celsius, Celsius and Fahrenheit scales converge, an interesting coincidence. At these temperatures, the atmosphere itself begins to behave differently. Water vapor H2O molecules floating in the air, which is normally a trace component of the atmosphere, but a significant greenhouse gas that helps trap heat and keep Earth warmer than it would otherwise be, would freeze out of the atmosphere almost entirely. The process is simple thermodynamics. The saturation vapor pressure of water, the maximum amount of water vapor air can hold at a given temperature, drops exponentially as temperature decreases. At room temperature, about 20 degrees Celsius, air can hold about 17 grams of water per cubic meter. At 0 degrees Celsius, only about 5 grams. At -20 degrees Celsius, less than 1 gram. At -40 degrees Celsius, essentially 0, fractions of a gram. Any water vapor in the air would condense and freeze, falling as snow or frost. The atmosphere would become extremely dry, desiccated, with almost no moisture. And without water vapor to trap heat through the greenhouse effect, Earth would lose one of its major mechanisms for retaining warmth. This would accelerate the cooling even further, another feedback loop, driving the planet toward absolute cold. Carbon dioxide, another important greenhouse gas that normally makes up about 0.04% of the atmosphere or 420 parts per million, would begin to freeze at the poles. CO2 has a freezing point of -78.5 degrees Celsius at Earth's atmospheric pressure, at 50% dimming, with temperatures at the poles potentially reaching -100 degrees Celsius or lower. Carbon dioxide would sublime directly from gas to solid, forming dry ice on the surface. You've seen dry ice before. It's used for special effects, creating fog when it sublimes from solid to gas. On a frozen Earth at 50% solar output, vast fields of dry ice would accumulate at the poles, white-ish solid CO2 mixing with water ice. As CO2 freezes out of the atmospheric pressure would drop. Earth's atmosphere normally has a surface pressure of about 101.3 kilopascals, or about 14.7 pounds per square inch. CO2 makes up only 0.04%, so freezing it out wouldn't dramatically change the pressure, maybe a drop of 40 pascals or so, negligible. But combined with water vapor condensing out and other effects of the extreme cold, the atmosphere would thin noticeably. Breathing would become more difficult even if you could somehow survive the cold, because there would simply be less air, lower pressure, less oxygen available per breath. The oceans would freeze to significant depths. Not solid all the way to the bottom, the ocean is too deep, averaging 3.7 kilometers globally and reaching nearly 11 kilometers in the Mariana Trench. The deep ocean would remain liquid, insulated by perhaps 2 or 3 or 4 kilometers of ice above it and warmed slightly by geothermal heat from Earth's interior. The mid-ocean ridges, where tectonic plates spread apart and new ocean floor is created, release heat. Volcanic hotspots, like the one under Iceland or Hawaii, release heat. This geothermal flux averages about 0.1 watts per square meter globally, far less than the solar input of 1,361 watts per square meter under normal conditions, but still a heat source. But most of the ocean would grow solid ice, kilometers thick. The weight of all that ice would be immense, compressing the ice at depth into exotic crystalline forms that don't exist at normal pressures. Ice has multiple crystalline phases depending on temperature and pressure. The ice we're familiar with is ice IH, the hexagonal form that makes snowflakes. Under pressure, ice can transform into Ice 2, Ice 3, Ice 4, Ice 6, and so on, with different crystalline structures. Under the crushing pressure of kilometers of overlying ice, the ocean would be a strange layered structure of different ice phases, with only the very deepest water remaining liquid. Perhaps if the temperature and pressure conditions allowed it. On land, glaciers kilometers thick would cover the continents. The ice sheets that covered North America and Europe during past ice ages were typically 1 to 2 kilometers thick at their maximum extent. At 50% solar output, with far more extreme cold persisting far longer, ice would accumulate to depths of 3, 4, 5 kilometers or more. The sheer weight of that ice would depress the continental crust, pushing it down into the mantle beneath. Continents are made of lighter rock, granite, and other felsic rocks that float on the denser mantle rocks beneath. The ice load would push them down, creating deep depressions. When the ice eventually melted, if it ever did, those depressions would slowly rebound, rising back up over thousands of years. We see this effect today in Scandinavia and Canada, where the land is still rebounding from the ice sheets that melted 10,000 years ago. There would be no liquid water on the surface anywhere on Earth. None. The hydrological cycle, the evaporation and precipitation of water that drives weather and supports life, would become completely dead. No evaporation because water is frozen solid as ice. No water vapor because any vapor would immediately freeze and precipitate. No clouds because there's no water vapor to form them. No rain, no snow, except in the sense that frozen water and carbon dioxide already on the surface might occasionally sublime in weak sunlight and redeposit elsewhere. But this wouldn't be weather as we understand it. This would be a trace process, molecules occasionally jumping from solid to gas and back to solid, but on a scale so small it would be negligible. The sky would be dark, even at noon on the equator. With half the normal sunlight, daytime would feel like twilight or dusk. You know that soft, dim light you experience just after sunset or just before sunrise, when the sun is below the horizon, but its light still illuminates the sky? That would be what noon looked like with 50% dimming. Shadows would be dim and indistinct, barely visible. Colours would be muted, washed out. The sun would appear pale and weak in the sky, a ghost of its former self. You could probably look directly at it without hurting your eyes, though you'd still want protection. It would be recognisable as our star, a disk in the sky brighter than the stars, but only barely. More like a very bright moon than the blazing furnace you're used to. Any life that remained at this stage would be clustered around geothermal heat sources. Deep ocean hydrothermal vents where superheated water gushes out of cracks in the seafloor, heated by magma chambers beneath. These vents can reach temperatures of 300 to 400 degrees Celsius, hot enough to melt dead. The water is loaded with minerals and chemicals, hydrogen sulfide, methane, iron, sulfur. Specialized bacteria and archaea extremophiles evolved to live in these harsh conditions, derive energy from chemical reactions involving these substances rather than from sunlight. They don't photosynthesize, they chemosynthesize, and they form the base of a food chain that's utterly independent of the sun. Giant tube worms, some over 2 meters long, house these bacteria in their tissues and receive nutrition from them. Crabs, shrimp, fish, all adapted to the vent environment, feed on the tube worms and each other. On land, volcanic hot springs where groundwater percolates down is heated by magma and resurfaces as hot water or steam might support small communities of thermophilic bacteria. Yellowstone National Park, with its famous geysers and hot springs, hosts extremophile bacteria that thrive in water near boiling point. In a frozen Earth scenario, these would become the only places life could persist. Geothermal systems deep underground, where Earth's internal heat keeps pockets of water liquid even as the surface is frozen solid. These are the refugees, and the life there would be simple. Bacteria, archaea, single-celled organisms, no complex life, no plants because there's no sunlight for photosynthesis, no animals because there's no plants to eat, no photosynthesis-based food chain to support them, no fungi, no protists, nothing complex, just the most primitive, resilient forms of life clinging to existence in the last warm places. Humanity, if any survived at all, would live in fully sealed, artificially heated underground bunkers powered by whatever energy they could still access. Nuclear reactors if they had the expertise and fuel. You'd need highly enriched uranium or plutonium, not the natural uranium that's too dilute to sustain a chain reaction without moderators. You'd need people who understand reactor design, operation, safety, maintenance. You'd need replacement parts stockpiled because manufacturing would become impossible. Geothermal taps if they were lucky enough to be near a heat source, drilling deep wells to access hot rock or hot water, and using heat exchangers to extract that heat. But geothermal energy is limited. It's not infinite. You can extract heat faster than it's replenished, depleting the resource. They would grow food hydroponically under artificial lights, probably LEDs optimized for the wavelengths plants use most efficiently, the blue and red parts of the spectrum. Lettuce, tomatoes, beans, whatever crops could be grown in confined spaces with artificial conditions. They would recycle air, probably using algae or chemical scrubbers. Algae photosynthesize, consuming CO2 and producing oxygen, but they need light, which would come from the same LEDs. Chemical scrubbers use materials like lithium hydroxide to absorb CO2 from the air. They would recycle water with absolute efficiency, condensing every drop of moisture from the air, purifying wastewater through filtration and distillation. They would recycle waste, breaking down organic matter to extract nutrients, feeding it back into the hydroponic system. Everything would be a closed loop because there would be no ecosystem to rely on. No natural processes to process waste or produce oxygen or purify water. It would all have to be done artificially, which means it all depends on the technology functioning. And even in the best case scenario, even with perfect technology and unlimited energy, you could only support a tiny population. Maybe a few thousand people globally scattered in isolated bunkers with no contact between them, because travel on the frozen surface would be impossible. Maybe less. The psychological toll of living sealed underground with no windows, no natural light, no access to the outside world, no hope of ever returning to a normal life would be immense. Depression, anxiety, conflict. In close quarters with limited resources and no escape, even small disagreements could escalate into violence. The social fabric would fray, and even these last survivors would be on borrowed time because equipment fails. Reactors have finite operational lifespans, typically 40 to 60 years before they need major refurbishment or decommissioning. Parts wear out, seals degrade, pumps fail, electronics malfunction, and without a functioning industrial civilization to manufacture replacements, to mine new uranium, to process it, to fabricate new fuel assemblies, to rebuild reactors, the bunker's days are numbered. Maybe you get 1 generation, maybe 2 if you're careful and lucky, but eventually, inevitably, something critical would fail that you couldn't fix. And the bunker would die, the heat would stop, the temperature inside would drop toward the ambient temperature of the deep earth at that depth, which is warmer than the surface but still well below freezing. The people inside would freeze or suffocate or starve. Humanity would go extinct. Not immediately, not dramatically, but through a slow grinding attrition as one bunker after another failed over decades or centuries. The last humans might survive for a century or two after the 50% dimming, living in their underground prisons, maintaining their technology as long as possible, raising children in artificial light who never see the sun or feel wind or see a tree. And those children would grow up knowing they're the last generation, that when the reactor fails or the food system breaks or the air system stops, they will die and humanity will be over. Can you imagine that psychological burden? Living with the certain knowledge that you're the end of a species? That's a horror beyond physical suffering. And yet the sun would still be shining, dim and weak but still there, still visible as a pale disk in the black daytime sky, still putting out energy, just half what it used to, still technically alive as a star, still undergoing fusion in its core, converting hydrogen to helium, releasing energy, but not bright enough, not strong enough, not sufficient to keep its third planet habitable. Let's go to 75% dimming. The sun loses 3/4 of its brightness. Only 25% of its normal output remains. Earth's temperature would drop to perhaps -80 to -100 degrees Celsius or lower. That's -112 to -148 degrees Fahrenheit. At these temperatures, we're approaching the point where even nitrogen, which makes up 78% of Earth's atmosphere, starts to liquefy. Nitrogen has a boiling point of -196 degrees Celsius at normal atmospheric pressure. We're not quite there yet at -80 to -100 degrees Celsius, but we're getting close. In the very coldest regions, the polar areas, temperatures might drop low enough that you'd start to see nitrogen frost forming on the surface. Oxygen, which makes up about 21% of the atmosphere, liquefies at -183 degrees Celsius. Again, not quite at that temperature yet in most places, but close. The atmospheric pressure would drop dramatically as more gases condense out and fall as frost or liquid. Carbon dioxide, already long frozen. Water vapour completely gone from the atmosphere except for trace amounts that immediately freeze. What remains would be mostly nitrogen and oxygen that haven't condensed yet, perhaps some argon, which makes up about 0.9% of the atmosphere and has a boiling point of -186 degrees Celsius. Also close to condensing, but the total amount of gas in the atmosphere would be reduced. Pressure would be significantly lower than the normal 101.3 kilopascals, maybe 80 or 90 kilopascals. Breathing would become difficult even if you somehow survived the cold because the air would be thin. The sky would be nearly black even at noon on the equator. With only 25% of the sun's normal output, daytime would be a dim twilight at best. It would be a faint, pale disk, barely brighter than the full moon is today in our normal timeline. You could look directly at it without discomfort or eye damage. It would cast almost no shadows, maybe a faint outline if you stood in direct light against a white ice surface, but nothing like the sharp shadows you're used to. The earth would be illuminated by a ghostly twilight, a perpetual dusk that never brightens. Stars would remain visible during the day because the atmosphere would be too thin to scatter much light and the sun wouldn't be bright enough to wash them out. The sky wouldn't be blue anymore. It would be black or deep indigo, and stars would shine through it even while the sun was above the horizon. The Milky Way would arch across the sky. If you could somehow stand on the frozen surface at the equator at noon and look up, you'd see the dim sun, the black sky, and thousands of stars scattered across the darkness. The same view astronauts see from space or explorers might see on the moon. Earth's sky would look like space. Earth would be geologically dead on the surface. No weather, no wind, because there's no atmosphere to speak of and no temperature differential to drive air movement. No erosion from wind or water because there's no wind and no liquid water. The surface would be static, frozen, unchanging. No tectonic activity visible at the surface because the cold would extend deep into the crust, making rock brittle and unyielding. The surface would be a corpse locked in stasis, unchanging for millions of years unless disturbed by a meteor impact. Any heat at this point would come almost entirely from Earth's interior. The core is hot, about 5,000 to 6,000 degrees Celsius, roughly the same temperature as the surface of the Sun, but in a much smaller volume. This heat comes from two sources: primordial heat from the planet's formation 4.5 billion years ago, when countless impacts and gravitational compression heated the early Earth to molten, and that heat has been slowly leaking out ever since. And radiogenic heat from the ongoing radioactive decay of elements like uranium-238, uranium-235, thorium-232, and potassium-40 in the mantle and crust. These isotopes decay, releasing energy as radiation and heat. The half-lives are billions of years, so they'll keep decaying and producing heat for billions more years. That heat doesn't depend on the sun at all. It's Earth's own internal heat engine, and it will last for billions of years as the radioactive elements slowly decay and the core gradually cools. But that heat is deep. The core is about 2,900 kilometers below the surface. The heat has to conduct through thousands of kilometers of rock to reach the surface, and rock is a poor conductor of heat. The thermal conductivity of crustal rock is maybe 2 to 4 watts per meter Kelvin, meaning heat flows very slowly. With the surface as cold as at 75% dimming, with temperatures of -80 to -100 degrees Celsius or colder, very little of that internal heat would make it all the way up to the surface. Most would stay trapped in the interior, slowly leaking out over geological timescales, millions and billions of years, but making almost no difference to surface conditions. Life at this stage would be impossible on the surface or anywhere near it. The only possibility, the only theoretical refuge would be deep in the oceans if any liquid water remained miles beneath the ice, or deep underground in cavities warmed by Earth's interior heat. Hydrothermal vents at the bottom of the ocean floor, where the mantle heat emerges through cracks and fissures, might keep small pockets of water liquid under the pressure of kilometers of ice above. Or deep geothermal systems, kilometers underground, where hot rock heats groundwater that's trapped in porous layers or fractures. These would be the only places, and the life there would be minimal, limited, barely hanging on. A few species of extremophile bacteria, maybe some archaea, single-celled organisms eking out an existence in the darkness, powered by chemical energy from Earth's interior, completely independent of the sun. Humanity would be long extinct by this point. Any bunkers that somehow survived the 50% dimming phase would have failed by now. The reactors would have run out of fuel or broken down beyond repair. The geothermal wells would have cooled as heat was extracted faster than it could be replenished. The hydroponic systems would have failed as nutrients were depleted or contamination took hold. The social structures would have collapsed under the stress and despair. The last humans would have died decades or centuries earlier, depending on how quickly the dimming occurred and how well their technology held up. Earth would be left with only the simplest forms of life, clustered in isolated pockets deep in the ocean or deep underground, unaware of the frozen wasteland above, living in eternal darkness, sustained by the faint warmth of the planet's dying heat. And the sun, the star that once sustained a thriving biosphere with millions of species, complex ecosystems, conscious, intelligent life that could look up and understand what it was seeing, would still be visible in the sky. A dim point of light, a fading ember, still shining because fusion reactions are hard to stop once they've started. Even dimmed, the sun is still massive enough and hot enough at its core to continue converting hydrogen to helium, but barely. Not enough to warm, not enough to illuminate, not enough to matter. Finally, let's take it to the extreme. The sun loses 99% of its brightness. Only 1% of its normal output remains. At this point, calling it the sun almost seems like a misnomer. It would be a star, yes. Technically still our sun. The same object, the same ball of plasma undergoing fusion. The brightest star in Earth's sky from our perspective. But it wouldn't look like the sun. It wouldn't have a visible disk that you could see. It would be a point of light, perhaps as bright as Sirius appears to us today, which is the brightest star visible from Earth in our current timeline, shining at a magnitude -1.46. But just a star among stars. No warmth, no life-giving energy, nothing that would tell you it was once the center of a living solar system, the power source for a planet teeming with life. Earth's temperature would plummet to perhaps -200 degrees Celsius or even lower. That's -328 degrees Fahrenheit. At this temperature, the entire atmosphere would freeze and fall to the surface as layers of ice. Nitrogen ice, oxygen ice, argon ice, carbon dioxide had already frozen at much higher temperatures. Water vapor long gone. The atmospheric pressure would be essentially zero. Maybe a few pascals from trace amounts of helium or hydrogen that don't freeze at any temperature we're discussing here. Helium has a boiling point of -269 degrees Celsius, just a few degrees above absolute zero. Hydrogen boils at -253 degrees Celsius. These very light gases might remain as an ultra-thin atmosphere, but you couldn't breathe them, and they'd be so sparse as to be negligible. The surface would be in a hard vacuum or close to it. The same conditions as the surface of the Moon or Mars today. You couldn't breathe. There's no air. Even if you had a spacesuit to protect you from the cold and provide oxygen, you'd need to bring your own because there's none in the atmosphere anymore. It's all frozen solid on the ground mixed with the ice. The sky would be completely black. Utterly, totally black, even at noon on the equator, even with the sun directly overhead. No scattering of light because there's no atmosphere to scatter it. No blue, no clouds, no haze, no twilight gradation, just the pure black of the vacuum of space. Stars would remain visible everywhere, all the time, regardless of whether the sun was above or below the horizon. The Milky Way would stretch across the sky in glorious detail, unobscured by any atmospheric distortion, every star crisp and clear. The sun would be there among them, a bright point moving across the black sky as Earth rotated, but just another point of light, slightly brighter than the others, slightly yellower, but fundamentally indistinguishable from a bright star unless you knew where to look. At noon on the equator, if you looked up from the frozen surface, you would see the sun as a bright star. Not blinding, not even uncomfortable to look at, just a star. You could stare at it directly, though it wouldn't tell you much. It would cross the sky from east to west as Earth rotates, taking 24 hours to complete the cycle just like it always has, because Earth's rotation hasn't changed. Days and nights would still occur, though the difference would be minimal. Night would be black with stars. Day would be black with stars, and one slightly brighter star that's the sun. That's it. No real difference in illumination, and you would be looking at the source of all the energy that once made Earth a paradise. The fusion reactions still happening in its core, deep in the center where temperature and pressure are high enough to overcome the electromagnetic repulsion between hydrogen nuclei. Protons slamming together with enough force to fuse into helium. the mass difference releasing energy according to E = mc². The energy radiating outward, taking perhaps 100,000 years to work its way from the core to the surface through radiative diffusion and convection, then streaming out into space at the speed of light, but reduced to 1%, to almost nothing, to an output so pathetic, so insignificant compared to what it once was, that it might as well not exist. The surface temperature would be determined almost entirely by Earth's internal heat and the cosmic microwave background radiation left over from the Big Bang, which provides a baseline temperature of about 2.7 Kelvin or minus 270.45 degrees Celsius for empty space. Earth would be warmer than that because of its internal heat, the slow decay of radioactive elements and the residual primordial heat from formation. But not by much, maybe minus 200 degrees Celsius, maybe minus 220 degrees Celsius. Somewhere in that range, depending on the balance between heat production in the interior and heat loss to space. Cold enough that materials you think of as permanent, solid, indestructible would behave strangely. At minus 200 degrees Celsius, metals become extremely brittle. Steel shatters if you hit it with a hammer. Aluminum fractures like glass. Copper breaks. The crystal structures of metals change at low temperatures, making them fragile. Rubber becomes as hard as ceramic, losing all elasticity. Organic materials, any carbon-based compounds, are frozen solid, indistinguishable from rock. Water is harder than concrete, as hard as granite. You could build structures from ice that would be as strong as stone structures on normal Earth. The oceans, frozen to the bottom in most places, would be solid as bedrock. Perhaps the very deepest trenches, the Mariana Trench at 11 kilometers deep, the Tonga Trench at 10.8 kilometers, the Philippine Trench, the Kuril-Kamchatka Trench, perhaps these might have liquid water at the absolute bottom, heated by hydrothermal vents and insulated by kilometers upon kilometers of ice above. The pressure down there would be immense. At 11 kilometers depth, the pressure is about 1,100 atmospheres, over 110 megapascals, over 16,000 pounds per square inch. Under that much pressure, water behaves strangely. Its freezing point changes. The ice above would be compressed into exotic high-pressure phases, ice 6 or ice 7, with different crystal structures than normal ice. And maybe, just maybe, there would be liquid water at the very bottom, a thin layer pressed between the ice above and the rocky seafloor below, warmed by geothermal vents. And in that water, extremophile bacteria might survive, clustering around the vents, feeding on the chemicals, reproducing slowly, living in eternal darkness, under crushing pressure at the edge of survival. The last life on Earth. Not complex, not diverse, not aware of what they've lost, or that they're the end of billions of years of evolutionary history. Just simple cells doing what they've done for billions of years. Converting chemical energy into metabolism, persisting. Humanity would be extinct. Long extinct. The last human would have died hundreds or thousands of years earlier, depending on how quickly the dimming occurred and how long the last bunkers managed to hold out. There would be no traces left on the surface because the surface would be buried under kilometers of ice. Any structures, cities, monuments, all of it would be erased or entombed, crushed under the weight of ice or scattered by glacial movement. Future geologists, if there ever were any, if some other species somehow evolved or arrived from elsewhere, they might drill through the ice and find layers of sedimentary rock with odd chemical signatures suggesting past biological activity. They might find fossil traces if they knew where to look and could interpret what they were seeing, but they wouldn't find civilization. They wouldn't find art or writing or technology. All of it would be pulverized and scattered or buried so deep it might never be found. Earth would be a dead planet, a frozen ball of rock and ice with a faint residual heat deep in its core that will persist for billions of years as radioactive elements decay. And it would remain that way essentially forever, or at least for geological spans of time measured in millions or billions of years. The sun would continue to shine at its reduced output for billions of years more, because even at 1% it's still undergoing fusion, still a star. Even if a pathetic shadow of what it once was, and Earth would continue to orbit it, locked in the same gravitational dance, completing an orbit every 365.25 days just like it always has, but lifeless, dead. A monument to what happens when the energy source that sustains life fails. Now, let's step back from the abyss. Let's think about what we've just explored together. We started with the sun at full brightness, that brilliant orb in the sky delivering 174 petawatts of power to Earth, maintaining a global average temperature of 15 degrees Celsius, creating a stable climate that has allowed life to flourish for billions of years. We watched it dim in stages. At 1% we saw agricultural disruption and the beginning of cooling. At 5%, ice age conditions and civilization under severe stress. At 10%, mass death and ecosystem collapse. At 25%, near total extinction of complex life, the planet locked in ice. At 50%, a frozen wasteland with only bacterial life surviving in isolated refuges. At 75%, geological death, the surface static and unchanging. At 99%, a lifeless ball orbiting a fading star, atmosphere frozen, ocean solid, no trace of the paradise it once was. What does this tell us? What's the lesson we need to absorb? It's profound and it's simple. We are utterly, completely, absolutely dependent on the sun. Every breath you take, the oxygen came from photosynthetic organisms powered by sunlight. Every bite of food, the energy traces back to sunlight captured by plants or photosynthetic bacteria. The warmth you feel, that's solar energy, either directly as sunlight on your skin or stored in the atmosphere and oceans. The liquid water you drink, it's liquid because the sun keeps Earth warm enough. The air you breathe, its composition is maintained by biological processes that depend on the sun's energy. Remove the sun or even significantly reduce its output, and everything collapses, not slowly, not with time to adapt and find alternatives, but catastrophically, inexorably, completely. Within years, human civilization would be in crisis. Within decades, it would collapse. Within a century or two at most, Earth would be unrecognizable, a frozen wasteland where life, if it existed at all, would be reduced to primitive bacteria in isolated pockets. And here's the critical insight. This isn't some distant theoretical concern about an impossible scenario. It's a demonstration of fundamental dependence. We live in a narrow band of conditions, a narrow range of temperature, a narrow range of solar energy input, a narrow atmospheric composition, a narrow set of climate patterns. Any significant change to any of these factors and life as we know it ends. Not struggles, not adapts with difficulty, ends. Now you might be thinking, but this is all hypothetical, the sun isn't actually going to dim, and you're right. Let me explain why this scenario, while physically impossible in the way we've described it, teaches us something crucial about reality. Here's a comprehensive framework that makes all of this clear. A way to truly understand our dependence that astronomers and climate scientists use every day. It's called Earth's energy budget. And once you understand it, you'll never think about the sun, the climate, or our planet the same way again. Think of Earth as a bank account. Every second the sun makes a deposit of energy into that account, 174 petawatts, delivered as sunlight streaming across 150 million kilometers of space. That's the incoming energy, the deposits. Earth then spends that energy by radiating heat back into space as infrared radiation, the thermal radiation that all objects emit when they're warmer than absolute zero. That's the outgoing energy, the withdrawals. As long as deposits equal withdrawals, the account stays balanced. The temperature remains stable, climate patterns persist, life continues, equilibrium. But here's the critical part that most people don't realize. Earth didn't create this balance. We didn't choose this equilibrium. The balance was given to us by the accident of our distance from the sun and the sun's output, and we evolved to fit it. Our entire biosphere, every ecosystem from tropical rainforest to Arctic tundra, every species from bacteria to blue whales, every biological process from photosynthesis to respiration, all of it calibrated to expect exactly this amount of energy. No more, no less, this precise amount. Try to really grasp this, can you? The sun deposits 174 petawatts. Earth radiates approximately 174 petawatts back out as infrared. The difference between these two numbers, the tiny imbalance, determines whether the planet warms or cools. Right now, in our current timeline, due to human greenhouse gas emissions trapping some of the outgoing infrared, we're retaining about 0.5 to 1 petawatt more than we're radiating. That tiny imbalance, less than 0.6% of the total budget, is causing all the climate change we're experiencing. Melting ice, rising seas, stronger storms, shifting weather patterns, all from less than 1% of the total energy budget being out of balance. Now imagine what happens when the sun's deposit drops by 5%. That's not a 5% imbalance, that's a 5% reduction in the total budget. The sun delivers 8.7 petawatts less. Earth initially radiates at nearly the same rate because its temperature hasn't changed yet. The account goes into deficit rapidly. The planet cools to restore balance, radiating less as its temperature drops, but that new balance is at a much lower temperature. And as we've seen, even small temperature changes cascade into massive disruptions. This is the framework. This is how you need to think about our relationship with the sun. We're not independent. We're not self-sufficient. We don't have alternatives or backups. We exist in an energy balance established by our distance from the sun and the sun's output. Change either variable, and the entire system reorganizes around a new equilibrium. And that new equilibrium might not support life as we know it. Probably won't support life. Almost certainly won't support human civilization. The energy budget framework explains something else profound. It explains why small changes matter so catastrophically. People often ask, how can a degree or two of warming or cooling be such a big deal? We experience bigger temperature swings between day and night or summer and winter. The answer is that we're not adapted to arbitrary temperatures. We're adapted to this specific energy balance, this specific average global temperature. Our agriculture works within a narrow range. Our water cycle functions within a narrow range. Our ecosystems evolved within narrow ranges. Push outside those ranges and systems don't just work a little worse. They break down entirely, they cross thresholds, trigger feedbacks, and reorganize into completely different states. You can visualize this, can't you? Actually, no. You probably can't. And that's okay, that's normal. The human brain didn't evolve to think in terms of global energy budgets or planetary equilibria. We evolved to think about immediate local survival. Find food today, stay warm tonight, avoid predators. Our intuitions about energy and climate are local and short-term. The idea that every living thing on Earth depends on a precisely balanced flow of energy from a star 150 million kilometers away, maintained within a narrow range for billions of years, that's not intuitive. It's not something we can feel directly, but it's real, measurably, demonstrably, scientifically real. So why does this thought experiment matter if the sun isn't actually going to dim? Because it's not really about the sun. It's about understanding dependence. It's about recognizing how utterly reliant we are on conditions we take for granted. The sun is a main sequence star, specifically a G-type yellow dwarf. It's about 4.6 billion years old, roughly halfway through its stable hydrogen-burning phase. For the next 5 billion years or so, give or take, the sun will continue to fuse hydrogen into helium in its core at a steady, predictable rate. During this time, it will actually slowly increase in brightness, not decrease, as helium builds up in the core and changes the fusion dynamics. Over the next billion years, the sun will brighten by about 10%, which will actually make Earth too hot, not too cold, eventually boiling away our oceans. Then, in about 5 billion years, the sun will exhaust the hydrogen in its core, begin fusing hydrogen in a shell around the inert helium core, expand dramatically into a red giant perhaps 100 times its current diameter, engulf the inner planets including possibly Earth, and eventually shed its outer layers to become a white dwarf. But that's billions of years away, and it's not a dimming, it's a dramatic brightening and expansion followed by collapse. For the sun to dim the way we've been discussing would require something extraordinary and unprecedented, something that disrupted the fusion reactions in its core, maybe a massive influx of heavier elements, like iron, that poison the fusion process. But where would billions of solar masses of iron come from? There's nothing nearby massive enough. A passing star could gravitationally disrupt the sun's structure, but stellar close encounters are extremely rare in our region of the galaxy, happening perhaps once every several million years, and they wouldn't cause a slow dimming anyway. They'd cause chaos, ejecting planets from orbits, but not a gradual fading of the star itself. Could some unknown process affect the sun's fusion rate? Maybe something involving the sun's magnetic field, which drives solar activity like sunspots and flares? Or the convection currents in the outer layers that transport heat from the radiative zone to the surface? Theoretically conceivable, but we've studied the sun extensively with satellites. Helioseismology measuring vibrations that tell us about the interior structure, spectroscopy, analysing the light to determine composition and temperature, neutrino detectors measuring the neutrinos produced by fusion reactions. The models that predict how the sun works match observations extremely well. The sun's behaviour is predictable and is not going to spontaneously start dimming, so the scenario is physically unrealistic. The sun will keep shining steadily for billions of years. But the thought experiment matters anyway because it's not really about the sun dimming, it's about understanding the fragility of our existence. The sun will keep shining, but other things could change. Earth's orbit could be disturbed by a passing rogue planet, one of those wandering worlds ejected from their home systems and drifting through interstellar space. We've detected dozens of them through gravitational microlensing. If one passed close enough to our solar system, its gravity could perturb Earth's orbit, moving us slightly farther from the sun. The result would be similar to the sun dimming, even though the sun itself remained unchanged. We'd receive less energy per square meter because we're farther away. Temperatures would drop, the catastrophic cascade would begin, or consider asteroid impacts. A large enough asteroid, and we know they exist because we've catalogued thousands of near-Earth objects and seen the craters they've left on Earth and the Moon and other planets, could throw enough dust into the atmosphere to block sunlight for months or years. It wouldn't be permanent, but it would be a severe, temporary reduction in the sunlight reaching the surface. The dinosaurs went extinct 66 million years ago, after an asteroid about 10 kilometers in diameter struck the Yucatan Peninsula, creating the Chicxulub crater 180 kilometers across. The impact energy was perhaps 100 teratons of Talmul, about 2 million times more powerful than the largest nuclear weapon ever tested. The impact threw up so much dust and vaporized rock that sunlight was blocked for months or years, possibly decades. Global temperatures dropped, photosynthesis stopped or was severely limited. Plants died, herbivores starved, carnivores starved. The food chain collapsed from the bottom up. About 75% of all species went extinct, and that was just a few years or maybe decades of reduced sunlight from atmospheric dust. Not a permanent dimming of the sun, but the effects were catastrophic. Imagine if the reduction lasted centuries instead of years. Or consider supervolcanoes. The Yellowstone caldera in Wyoming, for example, has erupted catastrophically 3 times in the past 2.1 million years, most recently 640,000 years ago. When it erupts again, and geologists consider it a matter of when not if, though it could be thousands or tens of thousands of years from now, it could inject enough ash and sulfur dioxide into the stratosphere to block sunlight for years or decades. The eruption 640,000 years ago ejected perhaps 1,000 cubic kilometers of material. The ash would spread globally in the stratosphere, reflecting sunlight, cooling the planet. Global temperatures could drop by several degrees Celsius. Growing seasons would fail globally. Famines would be widespread. And this is a natural process that happens periodically on Earth, not hypothetical, real. Even human activity could theoretically reduce sunlight reaching the surface. Some geoengineering proposals to combat global warming suggest injecting reflective particles like sulfur dioxide aerosols or other materials into the stratosphere to bounce some sunlight back into space before it reaches the ground. If done carefully in small amounts, this might slightly cool the planet and buy time to reduce greenhouse gas emissions. But if done recklessly, if too much material was injected, or if we became dependent on it and couldn't stop even when we wanted to, it could trigger a cooling crisis. We could artificially dim the sun from Earth's perspective, reducing the energy reaching the surface below what life depends on. We could trigger an ice age through our own actions, and the sun, your sun, the star that makes your existence possible, will keep shining. Will keep delivering energy, will keep warming this planet, and as long as it does, life can continue, can adapt, can thrive, and we, blessed with consciousness, can appreciate it, can understand it, can protect it, can look up at the night sky with new eyes, seeing not just points of light but distant suns, perhaps nurturing life of their own. All reminders of the cosmic processes that made us possible. Thank you for joining me on this exploration of what would happen if the sun slowly went dark. If you found this valuable, if it changed how you see the sun, the earth, your place in the cosmos, a like or subscribe would mean a lot. It helps me keep making these deep dives into the nature of reality and our fragile existence within it. And remember, the sun is shining. It will keep shining for billions of years. You're safe. We are all safe. The energy that powers life flows steadily from our star. The conditions that allow our existence are maintained. We have time to live, time to learn, time to protect this world, time to appreciate the extraordinary gift of consciousness in a vast, mostly lifeless universe. Look up at the sun tomorrow with new eyes. See it not just as a bright light in the sky, but as the source of everything, the foundation, the power source, the reason Earth is alive, the thread holding existence together, and may you never take it for granted again.